As an early career mathematician myself, I'm very excited and very happy to have great early career mathematicians today to give interesting talks. So the goal of this session is to recognize new researchers who will potentially be future leaders in their respective research areas. This session is co-organized with Biji Wong. She is a postdoc at Max Planck Institute, and myself. I would like to pass it to Biji, so she will introduce our first speaker for today.
First speaker for this afternoon or evening, if you're joining from Europe, like me, is Corrine Yap. She's a 5th year graduate student at Rutgers. She works in the intersection of combinatorics and probability in topology and statistical physics. Today, she'll tell us about homeomorphs of hypergraphs.
Thank you so much to the AWM and especially to the organizers for having this. I'm very excited to be here. And I know this is supposed to be brief, so I'm setting up a timer for myself to make sure I stay on track. So let's get started. Let me talk about a problem that I'm interested in, probabilistic combinatorics, that has some interesting relationships with topology as well. So I'm going to start from scratch and first define what a graph is. When I talk about graphs, I'm talking about a set of these and a collection of edges, which are pairs of those vertices. So here you can see I've drawn an example of a graph, another famous one called the Peterson graph, where the black dots represent vertices and the colored lines between two vertices, those are my edges. For the purposes of this talk, the colors don't mean anything, but in other contexts, they certainly do mean something meaningful. And let me tell you about the classical problem that I'm interested in, which is a foundational problem in extreme combinatorics named after Paul Turan. And it says this: fix your favorite graph H, fix the number of vertices in your target graph. How many edges do you need to throw into your target to guarantee you start seeing copies of your favorite? So let's see an example. Let's say your favorite graph is a triangle, so 3 vertices and 3 edges between them. And let's say you want 5 vertices in your target graph. How many edges do you need to start seeing triangles? So for instance, if you have 0 edges, you don't have any triangles in your graph. If you have all the possible edges, 10, then you see more than one triangle. In fact, you see lots of triangles. So what happens in the middle? What happens, when does it switch from not necessarily seeing triangles to always having triangles? For example, if you have 6 edges, you can see here's an example on the left of a graph with triangles. And here's another one, but in fact, you don't always have to have triangles. So 6 is not quite enough because we can find a graph on 6 edges with no triangles. Now, if I put it up to 7 edges, okay, now I have some examples where each of them have triangles. And it turns out that 7 edges suffices. And this is a famous theorem by Mantell from 1907 that says, in fact, if you have more than n squared over 4 edges and n vertices, you must always contain a triangle. And this is tight. We know a triangle-free graph that has exactly n squared over 4 edges. Okay, so this Turan problem is well studied for different kinds of graphs, so not just triangles, but other other choices of your favorite graph. And we sort of know a lot about what we can do and what is difficult about this problem. So we want to try and generalize this problem, and I can generalize it in a couple of different ways to make it still interesting. And in particular, I can generalize to this sort of higher dimensional version of graphs that I'm going to call hypergraphs. So again, we have a set of vertices, but now I allow my edges to be arbitrarily sized subsets of vertices. So here I've drawn an example of a hypergraph where my colored lines again represent an edge each. And this is actually a 3 uniform hypergraph where each edge has exactly 3 vertices in it. And I can ask the exact same question, but now for hypergraphs. Fix my favorite hypergraph, fix the number of vertices in my target. How many hyper edges do I need to throw into G to start seeing copies of my favorite? Okay, and again, this is a well-studied problem. And again, we sort of know some things about it, and we also know the difficulties of this. So I'm going to generalize it one step further. And here's where the topology is going to come into play. It turns out that when you take a hypergraph and you just consider it as a collection of subsets of your ground set of vertices, you can associate it with an abstract simplicial complex, which really just means I'm taking each hyperedge and I take the closure under subsets. And I throw all the subsets of the hyperedge into my collection. And I call those sets my simplices, faces of my simplicial complex. So on the right, you can see that each hyperedge has become like a triangle along with some one-dimensional edges bordering it, along with the zero-dimensional vertices. And in fact, if I start with a 3 uniform hypergraph, what I end up with by doing this process is a 2-dimensional homogeneous simplicial complex. Homogeneous in every maximal face has the same dimension. So you can see on the right, every maximal face is a triangle, a 2-dimensional face. And again, I can ask the same question, but now the topological spin to it. So I fix my favorite k-dimensional simplicial complex S. I fix the number of vertices in my target simplicial complex. How many k-dimensional simplices, so triangles in the previous example, do I need to throw in to guarantee? Now I'm not requiring an exact copy of my favorite, but I'm allowing for a homeomorphic copy of my favorite. And really for this problem, we're thinking about homeomorphs as being triangulations of things. So I think about a triangulation of the disk is homeomorphic to the original disk. And so I'm relaxing my conditions a little bit. I know this problem is not as well studied, but there are some historical results about it. So we attribute it to folklore, but it can also be read off of results by Erdős, that actually if you pick your favorite simplicial complex S, you can find some lambda of S, some exponent related to S, such that you sort of need to get lambda of S close to the maximum number of simplices to start seeing homeomorphs of S. So we have this n to the k plus 1 factor here. That is just the order of the maximum number of k-dimensional simplices you would have on n vertices. And we're saying I can take like sort of a lambda of S defect off of that, and I already start to see homeomorphs of my favorite. But this is in relation to, this is, you know, a lambda for the specific favorite simplicial complex that you pick. So an interesting question is, can you find some, what we call a universal exponent, lambda sub k, that only depends on the dimension of your favorite, and it does not depend on the specific structure of what you pick as your favorite simplicial complex? Can you find some universal exponent that lower bounds all of these individual exponents for your individual simplicial complexes? So this is the main question that I'm interested in. And there are some results for this question in lower dimensions. For instance, this is actually a graph theoretic result by Nadeau, who didn't word it in terms of topological Turan problems, but said lambda 1 equals 1. In his words, linearly many edges guarantee a subdivision of your favorite graph. And so that's the graphical version of this topological question. In 1973, Brown, Erdős, and Schoch showed the exact exponent for specifically the 2-sphere. So they said n to the 5 halves guarantees a copy of the 2-sphere, and it's typed up to constants. And more recently, what sort of what jump-started, you know, my interest in this question was a paper by Kivash, Long, Narayanan, and Scott, who found the lower bound for the universal exponent in 2 dimensions and said that was 1/5. And a few months later, this group, Kupovsky, Polyansky, Toman, and Zakharov, actually showed 1/2 is not just correct for the 2-sphere, but for any closed orientable surface. But the question remains, what about in higher dimensions? And so this is joint work with Jason Long and my advisor, Gab Narayanan, and we showed that this universal exponent exists actually in every single dimension, not just in 2 dimensions, and not just in 1 and 2 dimensions. Okay, so that was our main result. And further steps in this problem would be defining a matching upper bound for this universal exponent. And maybe looking at the k-dimensional sphere would give us a hint as to what the correct answer is, since the 2-dimensional sphere seems to tell us what is supposed to happen in 2 dimensions. And this would involve knowing things about simplicial spheres in higher dimensions. All right, so I'll end there. Thank you.
Our next speaker is Micah Henson. She is a graduate student at the Department of Applied Mathematics at the University of Washington. Her research interests are optimal control modeling. And actually, I'm ears and eyes here because she has a very interesting title, which is Maximizing Happiness in Marriage. So I welcome everyone to, to listen to it.
My name's Micah. I'm a 5th year at the University of Washington in Applied Math. And today I'm going to be talking to you all about maximizing happiness in marriage. So a little bit of context, around 15% of US marriages end in divorce, and this is a 50-year low. And previous research to explain these rates focused on differences in personality and communication with varying levels of success, but researcher John Gottman took a different point of view. So he interviewed couples and he had them discuss a problem in their marriage. And he identified 5 interaction styles: validator, avoider, volatile, hostile, and hostile attached. So validator, avoider, and volatile are both low-risk couples, and hostile and hostile detached are high-risk couples. And he quantified these interaction styles using a system called the rapid couple interaction scoring system. And with this method, he was able to predict with an accuracy of 94% whether or not the couples would be married or divorced in 4 years. So Gottman worked with some other mathematicians in 95 and attempted to develop mathematical theory behind their work. So they wanted to come up with a model that simulated what he was seeing in the lab with the interviews. And they came up with the discrete model and concluded that marriages that begin unstable dissolve because of an inability to adapt to a stable interaction style or a low risk interaction style. So my advisor Tung took that model and made a continuous time model representing the positivity of each spouse over time. And I take that model and turn it into an optimal control model. So here's the model. Well, at least the earliest iteration of the model. The goal is to maximize the happiness of spouse 1, subject to these differential equations here. And these equations represent the positivity of each spouse. And the X bars represent the natural disposition of each spouse, and R represents the rate of return to your natural disposition. So this function is made up of the influence state and then the influence state, which is the second part here, which is our control U, which represents kind of the ability of an individual to change how much they let their spouse influence them with initial conditions. And the second equation is the same, except in this simplified version of the model, we only have the response of the influence function of X2 to be fixed. And that's why we're only trying to maximize one person's happiness, because that's the only person we're allowing their response to change. So this is a standard optimum control problem. It looks a lot like the problem I just showed you, but I'm using this to show you how we approach optimal control problems. Basically, you use Pontryagin's maximum principle. And it says that if U star and X star are optimal for our problem, then there exists adjoint variable lambda such that this is true. So this inequality here is the Hamiltonian. And the Hamiltonian is made up of the integrand from the objective functional plus the adjoint times the state variable. And the adjoint is defined as the negative of the partial derivative of the Hamiltonian with respect to X, and it's subject to a transversality condition that at the end of time, it's 0. So the optimality condition is basically you want to maximize your Hamiltonian, find the partial derivative of your Hamiltonian with respect to U. And this is just like what you see in your calculus classes. You know that the maximum occurs where the derivative is 0, or it occurs at the boundary. And that's actually what we have in my case, because there is a linear dependence on a control. So instead, we take that optimality condition and call it a switching function. So your optimal control is the minimum when your switching function is negative, and it's the maximum when your switching function is positive. And so here is applying all of that to my problem. We get the Hamiltonian, which is the integrand from the objective functional, plus our first adjoint variable times our first state equation times our second, plus our second adjoint variable times our second state equation. And our optimality condition is lambda 1 x2. So our optimal condition our optimal control is Umin when lambda 1 x2 is less than 0, and Umax when lambda 1 x2 is greater than 0. So here is a numerical solution for some toy parameters. And in this example, we have a couple whose spouse 1 is natural disposition is positive, but it's just barely positive. And our second couple, the second person in the relationship has a fairly negative natural disposition compared to the first person. And if you look at our state solution, at the end, they end up both being positive. So in the end, their marriage is happy, and which is kind of not expected, and not unexpected, but rather they're able to overcome spouses two's overwhelming negativity. And that solution is characterized by these 3 switches in the control. So at least from the initial conditions I gave it in this example, which I had spouse 1 being negative and spouse 2 being positive. They're both able to end up in a positive, happy marriage. Well, that's pretty much it. So thanks to my advisors and to the organizers for having me.
Now it's time to introduce our next speaker, that is Tracey Oellerich. She's a graduate student at the Department of Mathematics at George Mason University. Her research interests are math biology and nonlinear conservation law. The title of her talk today is Singular Jacobsians and Their Effect on Adaptation in Biological Networks.
Hello, everyone. As mentioned, I'm going to talk to you about singular Jacobians and their effect on adaptation in biological networks. This is actually research funded through the Industrial Immersion Program at George Mason University through the George Mason Provost. So the first thing I'm going to go over is just some basic terminology. So what exactly is a biological network? And these are really just graphs. They're systems formed by the interactions of a collection of molecules that are interacting. So this could be like proteins, as we can see here with the picture of the EGFR, the epidermal growth factor receptor network, which is essentially just a bunch of proteins interacting with RNA transcripts, genes, combinations, that sort of thing. And what we're looking for here is these are networks that we know somehow they're adapting to some sort of change you're putting to the system. So this could be you're applying a drug to, say, this GAP protein right here, and somehow it's taking that and it's adapting to the drug, so the drug's no longer useful. And within these networks, we have nodes, which are essentially the proteins or the genes, the RNA transcripts, whatever's in the network. So these are the entities that will encode or transmit those biochemical signals. And they can undergo changes in activity due to the influence of other nodes. So this could be one node will inhibit the production of another, or one node could promote the production of another node, so we can get more of the other stuff. And when we start talking about adaptation, in particular, we're looking at robust perfect adaptation as described by Arajo and Liotta. So when we start talking about robust perfect adaptation, we're looking at biological systems in which the network itself will generate some sort of output that's always returning to a fixed reference level. So a fixed steady state whenever we change that input stimulus, and we don't have to worry about tuning system parameters. So as you can kind of see with this graph here, it's just a very simple example where I have a step input function. So this could be increasing a dosage of a drug over time. And every time I increase the dosage, the differential equations do react, everything adapts. Reacts, but somehow it ends up going back to a fixed reference level even after I make all these different changes. So that's what we're essentially looking for. So to start off with, we're going to do the mathematical definition. I'm going to keep it fairly simple. So we start off with a signaling network composed of n nodes. We're going to let one node be the input and one node be the output node. So the output's the one we're actually checking for adaptation to see if it's adapting to a change. And we can actually define this system by a series of differential equations given here. And what we're really interested in is looking at how these nodes change with respect to the inputs. So we're going to start by looking at Jacobians. And the first thing we're going to do is taking the differential of the system at the steady state. Assuming one exists, we're always just going to assume that. Sometimes it might not be possible though, for some given input, which we end up with this equation right here. And to check for adaptation, like I said, we want to know how the nodes themselves are reacting. How are the proteins reacting to changes in the input? So the very first step we need to do is isolate that dp star term. So in order to do it, we have two cases to consider. The first one is we have a non-singular Jacobian. We can invert it This is addressed very well in Arajo and Liotta. And the second case is the one that I was interested in. Here we're looking at a singular Jacobian, so we can no longer invert it. What exactly can we say in this case, and why does it occur? So case one, like I said, Arajo and Liotta went through and they did a very fantastic job of discussing this. And they ended up with some conditions that you can use to find out if the system exhibits RPA or not. And then for our work, we took their idea and now we tried to fit it with a singular Jacobian. And it does work. What we ended up doing is using the Moore-Penrose pseudo-inverse to essentially create an inverse per se of that Jacobian. And then we went through and solved the system similarly to how they did in Arajo and Liotta. And we end up with this equation right here, where you can actually, if you can satisfy this equation, then you can show that the system exhibits RPA. The big question then was, where exactly will we see singular Jacobians? It's not very common to see that sort of thing. In biological networks, you want to assume stability and you want to assume that everything is stable and we don't have any center subspaces or anything like that. So we did actually find a few examples. The first one, it's a very simple one. It's the Volpaire network, and it's a system of 3 nodes, X, Y, and Z. And in this case, we have a linear conservation law within this network. And if we go through, look at the Jacobian of the system, everything looks okay. But if you actually look at the Jacobian and really examine the different rows, you see that they obey that linear conservation law. In this case, row 1 plus row 2 plus row 3 has to equal 0. So we have that determinant of the Jacobian is equal to 0. However, this system, again, we've seen that the Jacobian is 0. And the reason this is because that linear conservation law. So here we just have a very simple proposition that shows that if we have a system and it has a linear conservation law, for all time, that determinant of the Jacobian has to equal 0. And it's interesting that for linear conservation laws, we see that it's for all time. If we look at something a little more complicated, so consider a non-linear conservation law. These ones don't pop up as often, but it's still a case we had to consider. So this is just an example from chemistry, the oxidation catalyst model from Elaina et al. And here it's, again, a 3-node network, but it has a nonlinear conservation law. If you go through and calculate the Jacobian, you see that last column is all zeros. So in this case, we know automatically that at the network steady state, this has a singular Jacobian. And we can, again, do a similar idea, writing a proposition. In this case, we're accounting for a nonlinear conservation law. And in this particular case, again, we do see the determinant of the Jacobian at the network steady state is 0, but it's only at that network steady state. Any other time, we could see it having some other value. But for adaptation properties, we're really only interested in the network steady state because we want to see what happens over a long period of time. And the last one was probably the one we found the most interesting. So within the network itself, so this is in accounting for conservation laws, we saw that if we had what we called special network structures, and this is just because we couldn't come up with a better term for it, these are essentially nodes within the network that are some function of other nodes within the network. So in this case, Pn is a function of the other n-1 nodes. And it's interesting to see that in this case, again, we do still have a singular Jacobian at the network steady state. And these nodes that are the combinations, they could be something like compounds within the network. It could be maybe this is how you're modeling a scaffold within a protein-protein interaction network. It could also be potentially just something you impose within the network itself to reduce the complexity of the differential equations. We saw that in a paper by Arajo where they had a 5-node network that really could be reduced down to 4 nodes. And in that particular case, the system exhibited adaptation in the 4-node network, and in the 5-node network, it still had RPA with our modified conditions, but we did see that it had a singular Jacobian. So that is everything. Thank you. Are there any questions?
So I'm really happy to introduce the next speaker, our 4th speaker. Her name is Elaina Aceves. She's a 6th-year graduate student at the University of Iowa. She works in low-dimensional topology. I feel close to my heart. And today she will tell us something about agal cycles of 3 braids.
All right, hello everyone, and thank you to the organizers for inviting me to speak today. As she mentioned, I'm definitely one of the topologists of the group, so I'm gonna have lots of pictures for you today. So to start us off, let's start with 3 braids. Where have you seen three braids in real life? Well, the traditional braid that you see when someone has long hair, that's actually an example of a three braid. I say the three braid. That is an example of a three braid. So essentially what we do is we kind of squeeze down those three sections of hair and consider that as three individual strands and really pay attention to the crossing information, which strand is going over or which is going under. And so the traditional three braid that we know, that can be seen as the three braid on the right-hand side. Now, how do I study these three braids mathematically? I study them as the mapping class group of a three punctured disc. Now, how do I do that? So let's look at the braid beta that's on the left-hand side of my picture here. So we have our three strands and I have two crossings. One of them is labeled with a plus, one of them is labeled with a minus. So a couple of different ways to see that orientation. One is to focus on the over strand and see, does it have positive slope or does it have negative slope? That can tell us if we're going to assign it a plus or a minus. The other thing we can do is if we were to actually try to grab these strands and rotate them to create that twist, if we rotate with our right hand, that's a positive crossing. If we rotate with our left hand, that is a negative crossing. So two different ways to see that orientation. Now, where does the three punctured disc come in? I am going to place discs and intersect it with our braid at three different levels, making sure to avoid the crossings. Now, all the disc sees is three punctures from those three strands. Now, secretly, if I label them 1, 2, and 3 from our original label on our strands, we know that at the second level set, strands 1 and 2 have actually switched. And then once again, we have this 1 and 3 have actually switched. But when you're staring at a disc, you don't really see that movement. So how can we keep track of that twisting? Well, let's actually place a curve on our disc. So on the right-hand side columns here, I have placed this curve around the right side dots. And so when we perform that positive twist, so we just locally grab those two dots and rotate, now our curve is going here instead of going here. And so we're going to keep track as we can keep performing these twists in our braid, we're going to get a more interesting looking curve in our resulting discs. So studying those curves is what I like to do. So what do we actually call these objects? They're going to be known as train tracks. So how do I get there? Left-hand side, that's the picture that you just saw on the previous slide. I'm going to kind of push all of these arcs and curves toward the upper half side of this picture, and then what we call zipping all this information. So for example, if I intersect right here, all these arcs, I see 4 intersection points. That information is encapsulated in this small arc with the label 4. Because it turns out once you start doing a lot of twisting, you're going to get a lot of arcs. So rather than having to draw like 12 parallel arcs to describe what's happening with this curve, we'd like to encapsulate all that information into a single object with these weights. So on the right-hand side here is a weighted train track. Now I do have more examples down below without any weights, but all the different kind of shapes that you can see with a 3 braid on this 3 puncture disc. Now, what kind of train tracks do I like to consider? I like to consider invariant train tracks. What are those? Now we just focus on the shape of the train track, perform all the twists that we have in our braid. And if we return to the exact same shape, now different weights, but exact same shape, that is an invariant train track. And so the ones that I like to look at, I call them type M and type W, because to me it looks like an M and a W. So those are the 2 that I focus on, and I only need to worry about those 2 for all the 3 braids. So what are we going to do with these invariant train tracks? We're going to perform what are known as maximal splittings. So we grab the edge that has the highest weight, and we want to split this up somehow to decrease that weight size. And we have 2 options depending on the weights on the other arc. So here, blue and black, you have a couple of options. So we start with our invariant train track, perform a max splitting, we get a brand new train track. We do it again, and we do it again, and we have this entire sequence going on that goes on forever. Why is this important? This leads into Agel cycles. So in 2011, Agel proved that eventually, we don't really know how far, but eventually you will get to a train track such that whenever you perform beta inverse, so you're actually doing like the reverse twists, he can show that you will return to a train track that you previously saw in a sequence. In particular, down below, these 3 figures are from a presentation by Dan Margalit. So our original braid beta that I showed you that only had 2 crossings, this is an example of an invariant train track. So he likes to put his punctures more symmetrically rather than in a horizontal line. But if you kind of slide these down, this looks like a letter M. So this is the invariant train track type. Eventually we perform our maximal splittings, get this entire sequence. You eventually obtain this diagram here on the right-hand side. Turns out if you apply beta inverse, do all those twists, you return to this train track. So this whole piece here that I'm kind of highlighting, that is our Agel cycle. So regardless of what 3 braid we have, we can always guarantee that this Agel cycle will exist. Now, what am I going to do with Agel cycles? This is where my research comes in. So I'm going to look at 2 braids, specifically that are related by a flight. Here I have a negative flight displayed. So these X, Y, and Z are just representing some number of crossings. It's known as a negative flight in this picture because of the negative crossing that you see in the bottom left and top right of these 2 pictures. What's changing to cause this flight is we're swapping the Z crossings with this negative. So these braids are distinct. So I want to discover how do these Agel cycles compare? Because if Agel cycles are a very strong invariant, they should be able to tell them apart. And I have found an infinite sequence of braids that you look at their negative flight, you compare their Agel cycles, and they're actually mirror images of each other, which is a very unexpected thing and a very particular relationship that so far I haven't seen. Otherwise, Agel cycles are very distinct. They look extremely different. It's very obvious, oh yeah, these are different, but they're extremely close and related by a mirror image. And I hit my 7-minute mark, so I will stop there. Thank you so much.
Now it's time to introduce our next speaker, who is Melanie Weber. She's a postdoc at the Mathematical Institute at the University of Oxford. She received her PhD from Princeton in 2021. Her research interests are machine learning and high-dimensional data analysis. The title of her talk today is Geometric Methods for Optimization and Machine Learning.
Yeah, thank you very much. And thank you very much for the opportunity to speak. So the research on which I give a brief overview today is motivated by the following observations. So in optimization and machine learning, the methods and algorithms that we typically use assume a Euclidean setting, so assume that our data lives in a Euclidean space. However, if we look at concrete applications that we encounter in machine learning, then that data often has an implicit or explicit non-Euclidean structure. So some examples are shown here on the slide. So we might encounter relational data such as graphs or networks with an intrinsic hierarchical structure. So they might look tree-like. Also in computer vision, we encounter compositional data. We encounter 3D shapes. And maybe to mention a third class, we often also encounter problems involving matrices. So either in the form of data matrices, like in fMRI data, for instance, or we might have a machine learning task that has a matrix valued subroutine, for instance, if we try to solve the matrix completion task. And in all of those examples, there are 2 questions that we could consider in the context of how we could use the geometric structure to design more efficient algorithms and methods for downstream machine learning applications. So first we could think about how we can characterize those features. How can we find a good representation for our data that explicitly encodes this non-Euclidean structure rather than trying to represent our data in the Euclidean space. And then once we have found a good representation, so we have represented our data on some Riemannian manifold with a geometric structure that aligns well with our data geometry, we can think about how we generalize those algorithms that assume a Euclidean setting to Riemannian manifolds. And our goal here is to develop algorithms or methods that are scalable so that we can actually apply them in practice, and that also come with provable guarantees so that we understand from a mathematical perspective in which cases those methods work very well, and also when not so, also understand the limitations. And in this context, I want to talk about 2 directions that I have worked on, mostly focusing on the second part, how can we generalize algorithms to Riemannian manifolds. And the first direction here is representing hierarchical data. So this is something that has recently gained a lot of interest in the machine learning community in the context of hyperbolic spaces and hyperbolic embeddings. So both trees, and therefore hierarchical data, as well as hyperbolic spaces, have the property that they have exponential volume growth. And this is in contrast to Euclidean spaces where volume growth is only polynomial. And what this allows us to do is to represent hierarchical data in a low dimensional hyperbolic space, whereas to gain the same representation accuracy, we would need a very high dimensional Euclidean space. And this low dimensionality is something that we can exploit in practice to design efficient algorithms, because oftentimes the complexity of our methods will scale in the dimension of the space that we are working with. And to just give one simple example of how such a generalization of algorithms could look like. So if we look at the very, very basic example of binary classification. So in the Euclidean setting, we might have two classes of data points here shown in 2D. And we assume that they are separable. And we want to learn a classifier by finding a separating hyperplane. And the algorithm that is shown here in the figure is the very classical perceptron algorithm. So in the Euclidean setting, this problem is very well studied for several decades. So this perceptron algorithm has been known since the 1950s. In the hyperbolic case, we could take inspiration from the Euclidean setting and design a similar algorithm. So here our data points would lie on the hyperbolic manifold, here shown in gray. And then what our perceptron style algorithm learns is a Euclidean hyperplane that intersects our manifold. And the intersection of those two will be our decision boundary, which we can use to classify our data points. And then we can also generalize the theoretical analysis and get similar guarantees to what we have in the Euclidean setting. And then without going into too much detail, but if we actually implement this algorithm and try it out on real data, we see that we also in practice see these advantages that we get from the low dimensionality and the good alignment of the geometry of our data, if it is hierarchical, and the hyperbolic geometry of our continuous space. And to give a second example, which was also shown on this initial slide with the examples, is optimization on matrix manifold, which we can use for matrix valued subroutines. So think of an optimization task over positive definite matrices. So if we look at the problem from a Euclidean perspective, we have to solve a constrained optimization task, but we could also reformulate the problem on the manifold of positive definite matrices. And in that case, we could use unconstrained Riemannian optimization tools. And there are many practical examples of matrix valued subroutines where such Riemannian methods have been used very successfully. So for instance, matrix completion that we initially mentioned, also synchronization of data matrices, dictionary learning, and so forth. One particular aspect that I'm interested in my work is geodesic convexity. So some of those examples that we've just seen have the interesting property that in the Euclidean setting, they are non-convex, but they are convex in the Riemannian setting. And if you're work in optimization, you know that convexity is extremely desirable because it gives us very nice global convergence guarantees. So if our problem is convex, we have a unique global optimum, which means that from any feasible initialization, our algorithms will converge to this unique global optimum. So that's highly desirable. So if by this reformulation of the problem on a Riemannian manifold, we can gain convexity, then that is super helpful in practice. And a little bit more concrete on the kinds of problems that I've been working on. So I've been focusing on constrained Riemannian optimization, which means that, again, we have some function defined on a Riemannian manifold, and we want to find its minimum, but we have the additional condition that our minimum has to lie in some compact region of the manifold. And with the classical literature that has been developed, this is a difficult problem to handle. since handling such constraints is, especially in the manifold setting, much more complicated than in the Euclidean setting. But it turns out that one of the very popular algorithms that has been used in Euclidean setting, the Frank-Wolf algorithm, can be generalized to Riemannian manifolds. So there are ways of generalizing the key components of this algorithm. And we can also recover similar theoretical guarantees to what we have in the Euclidean setting. Thank you.
I'm happy to welcome our next speaker, Nicolle González. She's a postdoc at UCLA. She works in representation theory and low-dimensional topology using combinatorial ideas. And today she will talk about categorification and a revelation of hidden structures.
All right, so my talk today is about categorification and a revelation of hidden shadows. And so let's start with, well, what is categorification? So first of all, categorification it's not a machine, right? So it's really kind of a dogma in the sense that it's the realization that you can take traditional structures that we see and just think of them as shadows of a far richer theory, you know, some sort of higher level in some sense. And the idea behind it is that you want to take, for example, sets, whatever it is you're working with, and think of them as categories, right? Construct some sort of category that recovers what your original thing is. So in this way, elements that you're dealing with in your original set become objects in a category, right? Relations and equalities that you have in your set, for example, x equals y, whatever x and y may be, then become morphisms in your category, right? So no longer do you say your object x is equal to your object y, right? You have some sort of morphism connecting the two. And if these things happen to be equal, you would expect this morphism phi that is encoding that equality to be an isomorphism, right? So you have an extra dimensionality of structure to work with. And it is precisely these natural transformations and these higher morphisms that give you the added information, right? So again, if you have some objects, some map phi and some map psi, let's say, that are going between x and y, then maybe you have a natural transformation relating the two. Maybe you have multiple isomorphisms and they're related via some higher structure, right? And all this higher structure is somehow not visible. It doesn't make any sense in your original classical object that you were studying. So a nice visualization of this is somehow to think of this as maybe the vector space. Maybe you're thinking about some sort of module or structure of a module, and maybe what you want to understand is really it's a categorical analog where these extra arrows are giving you some extra information. So really, in a nice nutshell, I would like to say that categorification is really about the existence and study of these higher extramorphisms, not about the objects in the category, but about the morphisms. But if I'm telling you how to construct a categorical analog, certainly we should be able to go back. So we have the somehow inverse definition, right, which is decategorification. And it's really just the process of going back and essentially forgetting information. How this is done is completely context dependent, however, because like I said, categorification is not a machine. There's no pre-described way where you feed me something and I give you some category that satisfies all these nice properties. No, not at all. So how you go back entirely depends on how you got the category in the first place. But certainly some things that we would like a categorification to satisfy in order for it to be a so-called good categorification is, well, we would want to somehow recover the original structure, right? This is supposed to be something that is more general, richer, but certainly that at least contains the original thing we wanted to study. We want it to provide new insights via the higher morphisms, right? It's very easy to say, all right, I'm going to construct some really complicated, convoluted categorical object that doesn't really tell me anything new about my original objects of study. In that case, it's not a very good categorification. You've achieved nothing. You've just complicated matters. Or you could have a very trivial categorification where these higher morphisms are just by default 0. Okay, that's not very exciting. It's not very interesting. So certainly you want that. And then you also want it to contain categorical analogs of any theory that is built upon the original, right? Okay, so essentially categorification is not contriving some complicated structure that returns the original, but offers nothing else, right? You really want extra information. And again, there's no machine. It really is very context specific because you have to invent the new structure. Okay, so some examples: vector spaces are a categorification of integers where you take dimensions. Representations of the symmetric group, for example, via characters categorify symmetric functions. The homology of topological spaces by taking graded dimensions categorify the Euler characteristic of topological spaces. It turns out that these categories are often depicted diagrammatically. So objects can be seen as, for example, points that if you tensor, you can view them as horizontal concatenation. Morphisms within these objects in this category can be drawn as string diagrams, where sometimes you keep track of over and under crossings. So this is harkening back to the talk that we just saw about braids, right? You essentially can draw these topological braid-like objects that are really encoding algebraic information about your category. If you have adjunctions, you can have things that go back, right? And depending on the algebraic structure, you can decorate these diagrams using arrows, using dots, using whatever you'd like to encode this algebraic information. But fundamentally, the idea is that the monoidal structures are drawn using this extra dimension. Right? So you have vertical concatenation, you have a horizontal concatenation, and that extra degree of freedom gives you more, it makes certain computations a lot easier. And that's really where this diagrammatic technology comes into play, right? That it really, really helps you computing things because that extra visual dimension makes a lot of relations very obvious. So for example, adjunctions or biadjunct functors, if you're trying to prove that algebraically, can get very complicated. Using pictures, it literally is just saying, all right, I can take a string and then stretch it. So you can apply topological intuition to these pictures. Okay, what does this have to do with knot invariance? Well, it turns out that it's very related. So a knot, right, we want to think about this as just a closure of a braid, right? So to every knot, we're going to just really focus on the braid, not necessarily the knot itself. And a fundamental question in low-dimensional topology is, how do we know if two knots are different or if they are the same? That's a hard question to answer, it turns out. So the idea is to invent invariants which can distinguish knots algebraically. Classically, this was done by assigning polynomials to braids. But it turns out that that is not a perfect way because sometimes you get two polynomials that are the same for different knots. So this was improved using homological methods, which essentially categorifies the polynomials to construct chain complexes. To every braid, you associate a chain complex. A fact is that these homological methods are actually stronger invariants. So what do? Well, I essentially think about or try to understand information about knots and in fact symmetric functions, which can be drawn as knots and braids by studying the homological algebra of these chain complexes in some diagrammatic category, right? In particular, I perform computations on these existing categories. I invent new categorifications of algebraic structures and their diagrammatics. I invent new pictures to describe these categorical objects, study their homological properties, and then try to answer questions about symmetric functions and the knots that correspond to them. Thank you.
So it's time to introduce our next speaker, that is Alice Nadeau. She's a postdoc at the Department of Mathematics at Cornell University. She received her PhD from University of Minnesota. Her research interests are applied dynamical systems and applications to climate. The title of her talk today is The Mystery of Earth's Synchronous Glacial Cycles.
Thanks to the organizers. I also want to acknowledge the the work of my two collaborators, Jim Walsh and Esther Widigassi, who worked with me on the project that I'm going to summarize here. We're going to start by deconstructing the title. So first we're going to talk about what characterizes Earth's glacial cycles. So right now, this is what Earth looks like in terms of ice. But 18,000 years ago, the story was completely different. We had large land glaciers on North America and Northern Eurasia, as well as extensive sea ice marked by blue here in the North Atlantic and North Pacific. In the Southern Hemisphere, we had the continent of Antarctica covered by glaciers, as well as extensive sea ice in the Southern Ocean. The reason we know this is because of data that scientists have collected from coring ice in Greenland and in Antarctica, as well as taking cores of ocean sediments in the Pacific and Atlantic Oceans. One of the main characteristics that we're going to talk about are the synchronous evolution of the ice caps on Earth. So what that means is, as the glaciers are evolving in the north and the south, they're either both, broadly speaking, moving towards the equator or melting back towards their respective poles. That's what we mean by synchronous. Another thing that we're going to be looking for in this study is to capture the similar behavior to what we see in these core records. So this is data from one of the sediment cores. And as so somewhat unintuitively, less ice is the top of this plot and more ice is moving down. But as the glaciers grow, they're growing very slowly and not monotonically. And then when they reach a maximum, such as what we would see here, they melt back really quickly to the current configuration, similar to the current configuration of ice that we have today. And we call that pattern a sawtooth pattern. So the very slow growth of the glaciers and then a very quick melt back when they reach their maximum. Okay, so those two things we're going to be looking for: the sawtooth pattern in sort of ice volume on the surface of the Earth, and then also this synchronous behavior of the location, the latitudinal dependence of the ice caps. All right, so what's the mystery? We're actually going to go back to that last picture and look at the differing geography at the poles. So in the North Pole, we have the Arctic Ocean surrounded by land. And in the South Pole, we have the exact opposite. We have the land of the Antarctic continent surrounded by water. And the mystery comes from the differing physics governing the growth and decay of glaciers on land versus the growth of sea ice in the water. In particular, as glaciers grow on the land, they become more unstable and more susceptible to exterior forcing, such as increased energy coming from the sun. And so when they're this big, when they extend down to Chicago and into the Finger Lakes region, which is where I am, they're really susceptible to these other external forces. Okay, but because of this differing geometry, we wouldn't really expect them to be evolving in the same way, especially because we have water surrounding the landmass of Antarctica on the right. All right, so that's our main question. Why are these glacial cycles in sync over these long timescales of 100,000 years? We're going to use mathematical models to help us understand this. We're going to come at it from a perspective of what is the bare minimum we need to capture these characteristics, the sawtooth pattern in mass and the synchronous evolution in latitude. So we definitely need mass, and we definitely need latitude dependence in the north and south of our ice sheets. We're also going to need temperature. That's going to capture some of these other behaviors that we are thinking about, like energy from the sun. And so these are our main variables that we're thinking about, and we're going to watch as they evolve in time. So we need to think about their derivatives. And for the moment, we're just going to think about two of them, just the location of the latitudinal dependence of ice in the northern hemisphere and the mass. So normally when we are looking at differential equation models, one thing we can think about is the vector field. And as we watch how these variables change in time, we can pick a point and just follow the arrows to tell us how they evolve. So if we're thinking about a model that describes the retreating glaciers, we're decreasing the latitude dependence of our Northern Hemisphere glaciers, and we're also decreasing the amount of ice at a particular time. The problem arises because the equations that describe the physical properties of the glaciers aren't physically relevant in this whole eta latitude mass space. And so if we're looking at the evolution of the glaciers, we run into this line, which is a barrier telling us your equations don't make sense anymore on the other side of this line. And in fact, there's a whole different set of equations that tell us what should be happening in this other space. And other way. And conceptually, they might look something like this. So if we retreat for a while, we reach this barrier where we can't retreat anymore. And then it's time to start growing the glaciers again. And so first the ice line grows, the latitude at which the ice is at, and then also the mass follows. The tricky analysis part comes with how do we interact with this line with our differential equations? And if we apply the appropriate techniques, we can figure out how to cross the line and follow this oscillation in our vector fields. And when we move this up into the four-dimensional space that all four of our variables that we're tracking live in, we actually recover exactly what we were looking for. So synchronous evolution of our northern and southern ice caps. This is not to scale. And then also a sawtooth pattern in the mass of our ice in the Northern Hemisphere. And that's it, thank you.
We introduce our next speaker, who is Perona Dutta. She is an Arnold Ross Assistant Professor at the Department of Mathematics at Ohio State University. She received her PhD from North Carolina State University in spring 2021. Her research interests are nonlinear analysis and PDEs, and the title of her talk today is Metric Entropy and Nonlinear PDEs.
So hi everyone, today I'm going to talk about my research on metric entropy and nonlinear PDEs, which is a joint work with Tien Kai Nguyen, Rossana Capriani, and Stefano Bianchini. So let me start by giving some motivation about the work. We consider a first order PDE, and given any bounded set of initial data C and t greater than 0, we denote by ST of C the set of all solutions to this nonlinear PDE with initial data belonging to C at time t. Now, the question which interests us is whether it is possible to measure the set of solutions to this PDE, and Lack suggested the use of Kolmogorov epsilon entropy for this study. So the topic of Kolmogorov epsilon entropy or metric entropy was introduced by Kolmogorov and Tikhomirov in 1959, and thereafter it has been used in several fields of study. For example, in probability and statistics, it is useful in measuring the covering number of different useful function classes. In information theory, it is a measure of randomness, so it is useful in predicting long-term behavior of random processes, and therefore is useful in machine learning and data analysis, modeling, sensitivity analysis, and so on. When it comes to dynamical systems, it provides a measure of the intrinsic instability of a system, and therefore is used in the study of stability and equilibria of biological models of aggregation. In PDEs, it provides a measure of the set of solutions to certain nonlinear PDEs. And when it comes to numerical analysis, it provides a measure of order of resolution and complexity of numerical schemes, and it has several other uses. So with all this in mind, let us now see the definition of metric entropy or epsilon entropy. Let E rho be a metric space and K be a totally bounded subset of E. For any epsilon greater than 0, n epsilon denotes the covering number, which is the minimal number of sets in an epsilon covering of K. And we define the epsilon entropy of K as the log base 2 of the covering number, and the symbol for epsilon entropy is H epsilon. In other words, epsilon entropy is the minimal number of binary digits needed to represent a point with accuracy of epsilon. Now, several instances like the metric entropy estimates have been established for several instances previously. For example, for an open ball in Rn, for n-dimensional Lipschitz functions, it's found to be of the order L over epsilon to the power n, where the functions are L Lipschitz. And it has also been found for one-dimensional BV functions where metric entropy estimates are of the order 1 over epsilon. Motivated by all of this, we wanted to study the metric entropy estimates for bounded variation functions in multidimensional cases. So we denote the set of bounded variation functions in multidimensional cases as FLMV, which is the class of all functions from 0L to the power n, taking values in R, and their total variation is bounded above by V. So along with Tien Khai Nguyen, I established the fact that entropy estimates in this case are of the order 1 over epsilon to the power n. And this result is useful in several studies. For example, it has been used in finding sample complexity estimates for multi-category classifiers, and also to find epsilon entropy estimates in scalar conservation laws for the case where the flux is not uniformly convex and has one inflection point. Now, further studies on conservation laws led us to the study of metric entropy estimates for generalized BV functions, because recent studies established that for the set of entropy admissible weak solutions to a scalar conservation law with weakly genuinely nonlinear flux, in that case, there is a bounded total generalized variation. So in that case, we considered the following set FCLV, which is the class of all bounded C total variation functions whose C total variation as defined here is bounded above by V. And these take values in a general totally bounded metric space E. And here C is a convex function such that C of 0 is 0 and C of S is greater than 0 for all S greater than 0. In this case, along with Capriani and Nguyen, we established that the epsilon entropy for this class of functions is of the order 1 over C of order of epsilon. And this was proved by using the notion of covering and packing in a metric space, and our estimates that we obtained involved the doubling dimension and packing dimension of the metric space. And thereafter, we used this result in order to establish metric entropy estimates for the set of entropy admissible weak solutions to a scalar conservation law with weakly genuinely nonlinear flux. And for the particular case where there are finitely many fluxes with polynomial degeneracy, this estimate was found to be sharp. Next, we studied metric entropy for Hamilton-Jacobi equations. So given the Hamilton-Jacobi equation, if we consider the set of Lipschitz initial data, and if we assume that the Hamiltonian is smooth, strictly convex, coercive, and uniformly directionally convex, then along with Bianchini and Nguyen, we established that in this case, the metric entropy estimates for the set of viscosity solutions to the Hamilton-Jacobi equation is of the order 1 over C to the power D of epsilon, where C is a function which depends on each. For this result, what we did was we established a BV bound on the set of slopes of backward characteristics. And we also established a quantitative relation between the W11 distance between two solutions and the L1 distance between the two slopes of corresponding optimal rays. And using that and the estimate for BV functions in n-dimensional cases, we obtained the result that we have here. Now, our study of metric entropy estimates open up a possibility of further studies. In some of the cases that we can see are metric entropy for the class of bounded total generalized variation functions defined on RD and taking values in a general totally bounded metric space. And we'd also like to find sharp estimates on the epsilon entropy of the set of weak solutions to the scalar conservation law in 1D for a general weakly genuinely nonlinear flux. Compactness estimates for Hamilton-Jacobi equation where the Hamiltonian depends on both X and T. And also metric entropy estimates for set of viscosity solutions to the Hamilton-Jacobi equation with a general strictly convex Hamiltonian. So these are some of the topics that I would like to have a look at in future. And that brings me to the end of my presentation. Thank you for your attention and thank you to the organizers for hosting this.